Hi, my name is Scott Simpson, and today we'll be talking about why is delta G negative for a spontaneous reaction. So throughout general chemistry and physical chemistry and many other chemistry courses, even in some biology courses, you're taught that if you have a negative delta G value, that it results in a spontaneous process, a process that will occur without any input of energy. But why is that? Why do you need a negative value? Well, today we're going to derive expressions explaining why that is true. Before we do that, we have to recall some previous equations that we have found. The first is the second law of thermodynamics. And one formulation of this is to look at delta S, or the change in entropy of a system. And what you can find is delta S of the universe must be greater than or equal to the change in entropy of surroundings plus the change in entropy of the system. Okay. Another equation that we're going to want to use is calculating the free energy of a system. Let's look at conditions where we have a constant temperature and constant pressure, because that will make our lives much easier. So Gibbs free energy. At constant pressure and constant temperature. So that's the easy general chemistry equation that pretty much everybody knows. Delta G is equal to delta H minus T delta S. Now this delta S that we're talking about right now, this is actually delta S of our system. So let's keep that in mind. Okay, one other thing that we need to bring back up is the definition of entropy. So this is the Clausius definition of entropy, where this comes from. Entropy can be defined as delta S is equal to Q divided by T. So this is delta S. It could be of a system, could be of surroundings. This Q could be the heat exchange with the system, or it could be the heat exchange with the surroundings. So now let's look at a situation. We said we have constant pressure. What we're going to do is we're going to look at heat exchanges at constant pressure. Basically, what we're trying to do is we're trying to find a relationship between this first equation and this second equation. We can already see that we found delta S of systems, so these things are connected to one another. But what about this delta S of universe and delta S of surroundings? To do that, let's first look at delta H here. Okay, so we have constant pressure, which is a big deal. We know something about the relationship between delta H and Q at constant pressure. We know that these two things are equal to one another. So this is the heat exchange of system at constant pressure. So we know the heat exchange is equal to the change in enthalpy of a system at a constant pressure. Okay, now let's bring some ideas from the first law of thermodynamics. So from the first law, we have shown that the heat exchange of our system, move that up, is equal to the heat exchange, the negative heat exchange of our surroundings. Okay, so now let's hop back up to this first equation. Let's try and define what delta S of surroundings would be. So delta S of surroundings Back from the Clausius definition of entropy, we would know that Q of surroundings divided by temperature is equal to delta S of surroundings. But the surroundings are really hard to measure because if you think about the system's the part of the universe we're interested in, the surroundings is everything else. So the surroundings are a vastly wide spot to try and measure things, which makes it very difficult to do. Okay, so let's try and change this into Q of system. If we do that, we have to use this relationship. The Q of the system is equal to the negative Q surroundings, or the Q surroundings is equal to negative Q system. So if we do that, we get this. Finally, we know at constant pressure that the heat exchange is equal to the change in enthalpy. So what we could say is at constant pressure, the change in entropy of surroundings missing an N in there, there we go, is equal to the change in enthalpy divided by the temperature. Okay, we're almost there. So we can find a relationship between these things. Now, let's jump back to our expression, delta G is equal to H minus T delta S. And we're going to do something strange. We're actually going to divide through by this negative T. For reasons you'll see why in a moment. So if we divide through by negative T, we get negative delta G over T is equal to negative delta H over T plus delta S. Okay, we know that delta S, this is actually the change in entropy of our system. And we've seen this expression before. Remember, recall that we just showed delta S of surroundings is equal to negative delta H over T. So this part right here, this is actually delta S surroundings. Delta S system. And we have negative delta G over T. Now this negative G divided by T, look, this looks eerily similar to that very first law of thermodynamics that we had, where we had delta S of the universe is greater than or equal to delta S of surroundings. Man, I just keep forgetting that M. Delta S system. Okay, so these two equations, we could set this to an equal sign, but these are the exact same thing. We have delta S surroundings, we have delta S system. That means negative delta G over T, that's actually equal to our delta S of the universe. So when we're talking about delta G, we're actually relating it to the change in entropy of the universe. And based upon the second law of thermodynamics, if we want this process to occur spontaneously, delta S of the universe has to be greater than 0. We have to be increasing the entropy to make this happen. For a reversible system, delta S is equal to 0. Okay, so finally, let's go back to our original question. Why do we need a negative delta G for a spontaneous reaction? So the question we're going to ask is, why is delta G negative for a spontaneous process? And what we're going to do, we're going to consider a reaction where delta G is equal to negative 12 kilojoules per mole at 298 K. So we've got a constant temperature, and we'll assume we have a constant pressure. In that case, we know negative delta G divided by T is equal to the delta S of our universe. So really, what we're trying to do is find a relationship between these two. So let's plug this in. We get negative 12 kilojoules per mole divided by our 298 K. The value we get is 0.040 kilojoules per mole times K, which is a unit of entropy. So in this case, we ended up with a positive value, S of universe. So when delta S of the universe is greater than 0, our delta G value has to be less than 0 based upon this relationship. So that's why when you have a negative delta G, this process is spontaneous. It all falls back to the second law of thermodynamics here that says that the entropy of the universe needs to ever increase for a spontaneous process to occur. All right. With that, I hope I cleared up some difficulties that you may be having with thermodynamics. I know it's not the easiest thing to study or understand. If you have any questions or comments, please leave them below or feel free to email and contact me. Thank you.